All right, AP Environmental Science. This is topic 4.5 out of Unit 2, and it deals with a topic called global wind patterns. So we're going to talk a lot today about wind, and directions that they blow, and some of the major air currents on the surface of our planet, which has an impact on living things as well. So if we're going to understand wind, we have to have a good understanding of air. So we'll talk a lot about air today and some of the qualities and properties of air. But this is kind of the essential knowledge that we have to know for this topic. It says global wind patterns primarily result from the most intense solar radiation, so sunlight actually drives winds, arriving at the equator, resulting in density differences and something called the Coriolis effect, which we'll talk about as well. So there's some pretty heavy vocabulary in this unit. So again, watch the video, maybe pause it if you need to, if it's getting kind of overwhelming to you, then continue with it. But ultimately, we need to understand the terminology and the concepts in this particular topic. All right. So again, if we're gonna understand wind, we have to again have some kind of an understanding of air. So, one of the things that most of us probably know is that hot air rises and cold air sinks, right? So, there's some reasons why this is. It has a lot to do with density, but just kind of remember that if the air is warm, at the surface of the planet, for example, it has a tendency to rise, and as it rises, it's going to cool, and cool air tends to sink. So what we get is this kind of a circulation pattern here. Okay, so just remember, hot air rises, cold air sinks. That's pretty much what you need to know about that particular concept. Now, another thing with air, as it rises and sinks, I want us to kind of understand sort of what's happening to the air as it's kind of going up and going down. So let's take this picture on the right as an example, and I really like this picture. So let's say we have a little balloon, okay, and maybe you guys have had like a helium balloon and you've let it go and it kind of floats up to the air, and maybe you've kind of wondered whatever happens to it. Well, let's imagine that we have this balloon. Let's say it's at the surface or close to the surface, and we know that again gravity kind of pulls things downwards towards the surface. But the other day we talked about air pressure. Remember that vertical column of air that we were talking about a couple of lectures ago? We know that the closer to the surface, air molecules are more tightly packed together. Okay, so if they're more tightly packed together, they're going to collide with each other. Remember, particles move. This is from chemistry class. So when they move, they produce more collisions. So this air that's in this balloon is fairly warm because of that reason. Now, we just said that warm air rises, and as it rises, it cools. We have a special name for this. It's called adiabatic cooling. So as that air rises, it's going to tend to get cooler. Now, the reason why that is because of air pressure. I want you to think about the pressure that's around this balloon. Okay, as the balloon rises, the pressure around it becomes less. So what happens to those particles that are in the balloon? It's not like there's any less of them. It's the same number of particles, but because the pressure around the balloon is less, those particles expand more. And if they expand, they're not colliding as much. And that means the air is becoming cooler. So the balloon is going to expand, okay? And again, the air molecules spread apart, less collisions, so the temperature decreases. So this is, again, what adiabatic cooling is. I want us to understand, again, what's happening to those molecules as they rise. Now, adiabatic warming is just the opposite. We just said that cold air tends to sink. So, as that balloon is rising, now sometimes, in fact, most of the time, when the balloon expands, it just pops. All right, but sometimes it doesn't. But it might rise to the top of this air column or whatever, and then once it gets cold enough, it'll start to drop down and sink. We call that adiabatic warming. So when the balloon sinks, the air pressure around the balloon gets greater. The molecules get more closely squeezed together, and then the temperature of those air molecules inside the balloon are going to get a little bit warmer. All right, so again, as the balloon sinks, it compresses. That means it gets squeezed by the air pressure around it. The collisions increase and the temperature goes up. So I want us to be able to contrast these two processes, adiabatic cooling and adiabatic warming. And it kind of goes along with hot air rising and cold air sinking, but I want us to know a little bit more than just that. And if you understand these terms of what's happening to that balloon, then you should be fine. Now, another property of air is something called water vapor capacity. Water vapor is basically just gaseous water, okay? And the temperature of the air sort of affects how much water vapor can be in the air. All right, this graph, even though it looks a little bit daunting, I guess, but um, I want to talk about how temperature affects water vapor capacity. And this graph here kind of, I think, does a good job of showing that. So let's say, for example, that we have, I don't know, let's say we have a nice warm summer day. Um, and let's say it's like in the mid 80s, maybe low 90s, which is about 30 degrees Celsius. 30 degrees Celsius is about 87 degrees Fahrenheit. So it'd be a pretty warm summer day. Now, over here on the y-axis, we have saturation point. On the x-axis, we have temperature in Celsius. But I want us to look at the unit here for saturation point. See where it says grams of water per meter cubed? Meters cubed is a unit of volume. All right, so imagine a box, 1 meter by 1 meter by 1 meter. A meter is about the length of your arm, maybe a little bit longer, depending on how small or large your arms are. But imagine a box of about a meter by one, 1 by 1 by 1. Okay, and these numbers on the y-axis represent how much water vapor that box can hold. Okay, so at 30 degrees Celsius, 86, 87 degrees Fahrenheit, what this graph is, if you kind of just go up to where it meets the graph and then go over, okay, we can see that at 30 degrees Celsius, our box of air can hold about 30 grams of water. That's all the water it can hold. Okay. Now, if the temperature cools, and remember, warm air rises, right? So imagine our box of air at 30 degrees Celsius. Imagine it's rising. And as it's rising, it's cooling. So let's say it cools off to about 10 degrees, so which is be much cooler, right? So if we go up to our graph and go over, we'll notice that the saturation point is only about 10 grams of water. So that means our box that once could hold 30 grams of water now can only hold 10. So I want us to understand this term here, okay? It's called saturation point. It says it's the maximum amount of water vapor that can be in the air at a given temperature. So at 30 degrees, again, only 30 grams of water vapor can be in our box. But if it cools, there's going to be less water vapor that can be held. So there's a difference there of about 20 grams of water vapor. Well, what's going to happen to all that excess water that can no longer fit in the box? It's going to come down to the earth as precipitation. Okay. So what I want us to understand is that when warm air rises, right, it's going to cool, and its ability to hold water is less. And then that excess water comes down to earth. So it says here when air temperature falls, like when it rises, saturation point decreases. These are the saturation points. Water vapor condenses, that means it turns to a liquid, and precipitation occurs. All right, this is a really important graph, I think, to understand because it kind of helps explain why, as warm air rises, not only does it cool, but it has more of a tendency to release water because the saturation point is falling. Okay, so a pretty important slide here. All right, now along with that is a property of air called latent heat. We call this latent heat release. This picture here, this is probably familiar to you, right? You might remember from chemistry class or maybe even like middle school science. These are your four phase changes, right? Melting and freezing, those two are kind of opposites, right? And then evaporation and condensation. The phase change that I want to kind of focus on is this one, okay? Because we just said that as warm air rises, the water that's in it condenses. So it turns from a gas to a liquid. Now, when that happens, okay, notice the arrow here is going from gas to a liquid, heat gets released. So the air actually becomes warmer when anytime that water vapor condenses into a liquid. So I want us to remember that, as this process, go back to this, as this process is occurring, as our temperature is dropping and that water gets released, it actually warms up the air when that happens. All right, this is the big reason why, like, if you've ever noticed, like, especially like in the summertime, like it'll rain and then like an hour later it's like really really warm and humid. That's because there's so much heat that gets released by this process. We call that latent heat. Okay, so make sure we know what latent heat is. All right, now for air currents. um, Before we get into this, I want us to know a little bit of I guess mapping. We need to be kind of familiar with a couple of different regions on the earth. These are latitude marks. Make sure we know, the equator. I think we kind of know where the equator is. But as you go north of the equator, okay, we tend to get these latitudes that increase, right? This is 30 degrees north. And then there would be, it doesn't show it here, but there's like a 60 degrees north. There's a 90 degrees north up by the North Pole. And same thing as you go south, like at the equator, 30 degrees south, 60 degrees south, et cetera, et cetera. Okay. So what you're seeing here is basically an area that's between 30 degrees north and 30 degrees south. All right, and there's a lot of area of our Earth that's in between those two particular latitudes. But the reason why these two latitudes are important is because this is something called Hadley form. Hadley cells are convection currents. Kind of remember when we talked about magma and like in the mantle, and as it rises, it circulates. Well, the same thing happens in the troposphere. Okay, this is the troposphere of the Earth, right? Where we live and where all of our weather occurs. But these air currents form, between the equator and 30 north and the equator and 30 south. And they are major driving forces of global wind patterns. So it's really important that we kind of know where they're occurring and kind of what drives them to occur, which we'll talk about on the next couple slides. All right, but again, just make sure we know where they're happening. So this picture here, I think, really gets in depth into how Hadley cells form. So what we've kind of done here is we've kind of tilted the Earth, I guess, sort of, to the point where like the equator is right here. Okay. So we're not looking at it, from the other view. We're kind of looking at it, I guess, kind of the opposite view. But you'll notice here that we have our equator. We have our 30 degrees north, and we have 30 degrees south. Now, one thing to remember about these two latitudes is that at 30 north and 30 south, this is where you find most of the deserts on our planet. Okay, so most of our deserts, in fact, just about all of our deserts, are found at those two latitudes. Now, there's a reason why, and we're going to talk about it when we get into this particular diagram here. Now, another thing about the equator is the equator. It's also known as the ITCZ. This is something that we'll talk more about in another lecture. But the equator is associated with climate that is always very warm and it's always very moist. So there's a lot of water vapor, in the air around the equator. Okay, if you've ever gone anywhere near the equator, hot and humid, like moisture in the air. Okay, so one thing that we know, right, about hot air is it's going to rise, right? So you'll notice these arrows going up, and you'll also notice at the top of this Hadley cell, you see where it says dry and cold, right? So everything is kind of just the opposite. Not only does the warm, moist air rise and it becomes colder, so that's why it's hot down here, cold up here, but it's also going to lose its water, right? So it's going to be moist at the surface. It's going to be very dry by the time it gets to the top. Okay, so at the equator, at that ITCZ area, okay, this is where the sun hits the earth. We have the most direct sunlight at this particular latitude than anywhere else on the planet. Okay. So again, there's a reason why that air is so hot near that equator. So again, the hot air rises. Again, as it rises, it experiences adiabatic cooling. It causes that air to expand and it cools. Okay. But again, not only does it cool, it also releases water. So we have a ton of precipitation near the equator. In fact, most of your tropical rainforests are found near the equator. Okay. So the warm air rises, it's cooling, but it's also releasing all that water vapor, and it's also releasing all that latent heat. So there's another reason why all that moisture is there and why it's so hot. Is all that latent heat gets released as well, and it causes that air to rise even more. Now, once it gets to the top of the Hadley cell, then it starts to fall. It doesn't fall straight down. It doesn't displace the air that's rising, but it tends to drop, towards a southern latitude or towards a northern latitude, which again would be 30 north or 30 south. All right, but again, as this colder air tends to sink, it's going to come closer to the surface of the Earth, but it's going to warm up as it sinks, right? So, for example, this dry, cold air at the top of the Hadley cell, when it drops to 30 south, it's going to be hot, dry air. Right? It doesn't have any moisture in it because all the moisture was dropped over here near the equator, but it does become warmer, but it doesn't have the moisture in it. Same thing here at 30 degrees north. That dry, cold air is going to sink. It's going to become warmer, but it's still very dry. This is why the climates at 30 north and 30 south are so warm and also so dry. There's just not any moisture in the air. But as that air moves back towards the tropics, it will pick up more moisture and it will just keep circulating again. So again, these are Hadley cells. I want us to understand what happens to the air as it's rising, what happens to the air as it's sinking, where is this occurring? Okay. Now this picture here, there are more than just Hadley cells. For example, here's the equator. Here you have 30 north, here we have 60 north, and here we have the North Pole, right? So again, here's a Hadley cell here, happening between the equator and 30 north. There would be another one on the other side. But then at 60 north, we have what we call Ferrel cells that happen between 60 and 30. We have what we call polar cells that happen between 60 and 90, which would be the North Pole. So we have these cells everywhere. The only one that you really need to know is the Hadley cell, but they do occur at different latitudes all up and down the Earth. Okay, so that's important to know. Now, the last thing that we have to understand about air currents and kind of what drives them is the spin of the Earth, the rotation of the Earth. I like this picture here because it's showing us the rotation, but it's also showing us that depending on where you are, you're actually spinning at a different speed. So, for example, at the equator, if you were standing at the equator, you would be spinning at about 1,600 kilometers per hour or about 1,000 miles per hour. Now, we don't feel that because the Earth is so big and we're so small in relation, but that's how fast the Earth spins. Now, if you go to a more northern latitude, you could keep going up and up and up. Look at what happens to the speed of the Earth. Depending on where you're standing, it becomes slower. And the same thing if you move to a southern latitude, it becomes slower. So depending on where you are, you're spinning at a different speed compared to someone else. Okay. This is called the Coriolis effect. All right. And it does have an impact on wind. Now, one of the things that I like to show kids is like, depending on where you're standing and where you're moving to, there will be a change in speed, and that will impact objects that get deflected. So let's say, for example, you're standing up here. I don't know, let's say you're up here in, I don't know, maybe North America somewhere. I don't know, maybe in Europe or something. And, let's say that you have this like superhuman ability to throw a baseball all the way to the equator. I mean, you don't have that ability, but let's say that you could. Okay. So if you can throw a baseball all the way down near the equator, remember, if the Earth doesn't spin, then that ball would just go straight down, right? But it does spin. And one of the rules is that if the object is moving from a slower speed to a faster speed, the object will always deflect to the west. So think about where this guy's standing. He's standing at a slower speed, right? And he's throwing it to a faster speed. That object will always deflect westward. Now, just the opposite would occur. Let's say you were standing down near the equator and you threw your ball straight north. So you would be standing at a faster speed. The object would be moving to a slower speed. That would deflect to the east. Okay. So if you look at these two examples, I think they explain pretty well why these objects are deflecting in certain ways, and it all is because of the spin of the Earth. Okay. So, these cells that form above the Earth, that the air is rising and then dropping, but it's also being deflected in certain directions, all because of spin. All right, so let's kind of go back to our Hadley cells, right? Hadley cells, the air rises at the equator, and then it drops to 30 north, and it drops to 30 south. But the air circulates back towards the equator. But what that ends up generating are these winds that sort of generate from the east and travel to the west. These are what we call trade winds. The trade winds that are, Up here in the north, we actually have a name for these versus the ones that are in the south. We'll come back to that in a minute. Now, we also said earlier that there are cells that form at 60 north. Oops. So there's a cell here that forms at 60 north, and it drops at 30 north. There's a cell here that rises at 60 north and drops near the pole. So we see the same type of pattern of air that's circulating here. Okay. So again, all of these wind patterns are generated all because of not only the Coriolis effect, but also because of the rise and fall of that air. The same thing happens down here in the south. Okay. You get the same type of thing that occurs. All right. So there are names again that we have for these winds. All right, these are probably the most important ones that you're going to have to know. These again are the trade winds. These are called the northeast trade winds because let's say, for example, this arrow right here, okay, it generates in the north, okay, it's north of the equator, and it generates in the east, and it travels to the southwest. So wherever it generates from is how we kind of name it. This is the southeast trade wind. So it kind of generates in the south, south of the equator, in the east, and it travels to the west. So just kind of understand the directions of these arrows, all right, the northeast trade winds, where they're located geographically, and where they're pointing to. Okay, so what ends up happening is you get this, if I get my little highlighter going here, change colors. You get this kind of wind pattern that flows along the equator in this direction because of an accumulation of all of these winds, both the northeast and the southeast. It just generally blows the wind this way. Now, these are along the surface. So if they're on the surface, any water that's on the surface tends to push that way as well. All right, that's kind of an important thing to remember as well. Now, there are also these other winds, these ones at the bottom and the top between 30 and 60. Those are called the westerly winds. All right, again, because they kind of originate in the west and they kind of blow to the east. And then we have what we call our polar easterlies. I can get this to come up here. There we go. Whoops. These are our polar easterlies. And again, they kind of originate in the west and they originate in the east and they travel to the west. But again, the two that you guys need to know, again, are these ones here. Those are kind of the most important ones. All right, this is another picture that kind of shows you the same thing. All right, again, but all of these surface winds, again, they all blow in a certain direction because of how the air is rising and how the earth is spinning. Okay, that's kind of an important thing. All right, guys, that was kind of a lot today. You might want to go back and watch it again, especially the part about the Coriolis effect, which can be a little bit confusing. All right, but I would be familiar again with this picture and kind of understand the direction that those winds are blowing. This picture here, I guess you could use as well. So, anyway, all right, guys, have a good day, and I will talk to you soon.